Now we are going to discuss about electric field due to continuous charges. Continuous charges means like as a charge given to that rod or plane sheets or spherical shells. Okay, these type of bodies in regular life we'll get only continuous charges. Not we don't get that point charges. Due to these continuous charges, for these continuous charges, how can we find out that field intensity, electric field intensity? To find out that one, we need a term that is called as also charge density. Charge density. The charge to the bodies we can give in three ways. Okay, if we give the charge to the body now along a single direction, that is called as also linear charge distribution. If the charge is given in a two ways along the x direction and y direction, like that in two dimensional way, if you give that charge, the charge distribution is called as a surface charge distribution. And if the charge given in three-dimensional way, that is a volume charge distribution. Okay, this charge distribution per unit dimension is called as our charge density. Depending on a charge distribution, these charge densities are classified into three categories. Number one, linear charge density. Linear charge density. Linear charge density means the charge given to the body per unit length is called as our linear charge density. Charge per unit length. Charge per unit length is called as a linear charge density. This we measure with a unit coulombs per meter. Okay. The next one is surface charge density. Surface charge density. This we represent with a sigma. Surface charge density means charge per unit area. Charge given to the body per unit area is called as a surface charge density. Formula of the surface charge density, charge by area. And volume charge density. Volume charge density we represent with a symbol rho. This is nothing but charge per unit volume. Charge per unit volume is called as a volume charge density. Surface charge density we measure with a unit coulombs per meter square. Okay, volume charge density unit is coulombs per meter cube. These are the three types of linear charge density. To find out the electric field due to the continuous charges, these are the terms we are going to study, so that's why I discussed these three definitions. Next, electric field due to the continuous charges. Okay, there are so many variety of questions are there. Here we are going to discuss some of the continuous bodies. Now we are going to discuss about field due to the linear charge distribution. Okay, line charge. Field due to the line charge. Here, field due to the line charge. For example, a charged wire is there. For this charged wire, okay, some of the charge we given that due to that charged wire, what is the field intensity in the different cases we are going to study. First, we are going to study about that electric field due to that line charge on the axis of the line charge. For example, consider this is the charged wire. Okay, is the axis of the charge Here this is the axis of the charge. On the axis of the line charge, I have taken one point P. At this point P, what is the field intensity? Electric field intensity. Now our topic is electric field due to the line charge. What is that line charge? Finite length charge it is, and we are finding the field intensity on axis. Now to solve this type of questions, first we have to measure the term how the charge is distributed. On this, the charge is distributed along the lengthwise uniformly. Now the total charge on this wire is, I am considering as a Q, and the total length of the wire is L say. Then charge per unit length, linear charge density is Q by L. Now the next step, divide this continuous charge into small element, and in that element one of the element I selected here. Okay, I selected one of the element here. This element length is, for example, dx. This element where I selected at a distance x from the selected point. Now this charge, line charge, on this line charge I selected a small element of dx length at a distance x. Now this small element behaves like as a point charge. Okay, first you find out the field intensity due to this small element. Next another element, next another element, next another element. Along the wire, on the total body, all the elements, if you all the elements due to the all the elements, if you find the field intensity and sum them, add them, you will get the total field intensity. Now I selected that small element. That small element is looking like as a point charge. What is the charge on this one? The charge on an element. Charge on the element. Charge on the element I am considering as a dq. Charge per unit length is lambda, and what is that length of the element? Dx. Hence the charge on the element is lambda into dx. Charge on the element is lambda into dx. Lambda into dx. That charge I am considering as a dq. Now find out the field intensity due to this small element dq. Okay, field due to the element. Field due to the element. Field due to the element I am considering as a dE. It is a point charge. No, due to the point charge, what is the field intensity at the point P? That is nothing but from the formula kq by r square. From that formula we can write k is 1 by 4 pi epsilon naught here, constant, and q, the charge of the element is dq, and distance, the distance between element and selected point is x we considered. Element and selected point is x we considered. Okay, that x square. Okay, now this dE is equal to k into dq is nothing but lambda into dx by x square. Okay, now this is the field intensity due to the small element at the point P. At this point P, the field intensity, it is a positive charge, and it acts away from the positive charge, hence dE acts away from it. Like this, all the elements arranging the field intensity at the point P away from the charges, all are acting in the same direction, hence we can add them. Okay, adding means here we are doing the integration. If you do the integration from A end to B end, okay, then you get the total field intensity. So on integrating we will get the total field intensity. Therefore total field intensity E is equal to integral dE from where to where we have to integrate? From A to B. Where is the A? A end is at a distance R from the point B, and B end is at a distance L, R plus L from the point B. Now we are doing the integration from R to R plus L. Now substitute the quantities. A is equal to integral K lambda dx by x square from R to R plus L. Okay, if you integrate this, K is constant, lambda is also constant. If you take outside, K lambda integral 1 by x square, we can write like as x power minus 2 into dx from R to R plus L. Now E is equal to K lambda into x power minus 2. Integration of x power minus 2 means x power minus 2 plus 1 by minus 2 plus 1. From where to where? From R to R plus L. Now this I am writing here. E is equal to K lambda into x power minus 2 plus 1 by minus 2 plus 1 is nothing but x power minus 1 by minus 1. Okay, so minus 1 by x from R to R plus L. Then E is equal to K lambda into 1 by minus 1 by R plus L minus of minus 1 by R. Now E is equal to K lambda into minus 1 by R plus L minus of minus plus 1 by R. Now E is equal to K lambda into 1 by R plus 1 by R minus E is equal to K lambda into 1 by R minus 1 by R plus L. This is the field intensity due to